Jai Hind everyone. I am Nikita Jaiswal from Civil Engineering Department, Ajay Kumar Garg Engineering College, and today I am going to give you lecture for topic types of similarities and model investigation. Okay, we have understood what is dimensional analysis and how we can analyze different parameters or any particular flow phenomena by using different model studies and dimensions methodology. Okay, in that we have studied how we can apply Buckingham Pi theorem or Rayleigh equation or Rayleigh theorem in particular fluid flow phenomena. Now, in next topic in this particular chapter, we are going to study what is model investigation. So, model investigation is simply what whenever we design or required to carry some experimental investigations on a particular project or structure or machine, then we test it on a particular model which may be in a symmetrical form to the prototype. Okay, so we what we need to study in this model investigation is that whenever we are trying to build a particular model of obviously from in a symmetrical manner with prototype, we need to understand, we need to keep in mind that some kind of similarity must be exist in between prototype and model. Okay, now this kind of investigations which involved experimental investigations are called model investigations. Okay, such investigations are essential for the problems which cannot be solved with theoretical analysis. So obviously there are analysis we need to do, we always prefer to do some analysis before going through any project. Okay, so the case where theoretical analysis is not possible, we go for model investigation. Now the small scale replica of actual project or actual structure is called model, and the actual structure is itself called prototype. Okay, now so similarity between the model and prototype, we need to discuss what kind of similarity must be there in between the two. Okay, so types of similarities we need to discuss. The first one is geometric similarity, the second is kinetic, and third is dynamic similarity. Now, what is geometric similarity? As the name suggests, that exists between model and prototype if the ratio of the corresponding length dimensions in the model and prototype are equal. Corresponding lengths, ratio of corresponding length, that means whenever we are going to talk about length divided by length in model and divided by length in prototype, let us suppose, for an example, let us suppose this is a dam. Okay, this is your actual structure, or you can say is prototype. Okay, and the dimension here, let us suppose this is BP, this length. When I am going to build any model based on this structure, so let us suppose I am designing with a base BM. Okay, and this is obviously, this is your model. Okay, and let us suppose this is height, so you can write it as HP, and height for model you can write it as HM. So what I'll say that ratios of corresponding dimensions in prototype and model should be equal. That means what I'll write now, HM divided by HP must be equal to BM divided by BP, or you can call it as the equal ratio, call it as HR, LR, or you can define it as, or you can say it as length scale ratio. Okay, so this is your LR. In a similar manner, you can define what is area scale ratio. So area scale ratio will be obviously LR square. Here you can see the derivation, of area scale ratio, and here is volume scale ratio, and volume scale ratio is equal to LR to the power 3. Okay. So this is how we can define length scale ratio, area scale ratio, and volume scale ratio. Now the second is kinematic similarity. We have gone through the first geometric. Now the second is kinematic similarity. Kinematic similarity exists between model and prototype if the path of homologous particles are geometrically similar and ratios of velocity and acceleration of homologous points are equal. What in this particular kinematic similarity, what they are trying to say, that if I take a corresponding point in prototype and a corresponding same point in model, when we are going to talk about the velocities at those particular points, or acceleration or at those particular points, or you can say the time taken by those particular points, see the ratios of this parameters should be in a particular manner. Okay, so when we talk about time, okay, so just take a time step in model and that particular time in prototype. So that ratio will be equal to your time scale ratio. Okay, what is now velocity scale ratio? As the definition suggests, that will be equal to your LR by TR, length ratio by time scale ratio. Okay. The same way acceleration, what how you can define acceleration? LR by TR square. Okay, this will be equal to your acceleration scale ratio. Now the next is discharge scale ratio. As the unit of discharge says meter cube per second, so you can remember in that way that the discharge scale ratio must be equal to LR cube by TR. Now the third type of similarity is your dynamic similarity. Now what is this dynamic similarity? This exists in between model and prototype if model and prototype, if they are geometrically and kinematically similar. Okay, then the forces along the homologous points in model and prototype, that must be equal. Okay, so how we are going to define it? Let us suppose, see, the name dynamic similarity says that there must be any type of forces involved in that particular model or prototype. Okay, and what are the forces that may be involved in a particular fluid phenomena? Maybe gravity force, maybe pressure force, maybe viscous force, maybe surface tension, maybe capillarity force, maybe or other type of forces. Okay, so when we are going to analyze all this type of forces, we need to remember, we need to understand what kind of force is there. Okay, so see here the type of forces that may be involved in particular phenomena, maybe gravity, maybe pressure, viscous, surface, and compression. Okay, compressibility force. Now take the summation of all the forces. See, for example, here you can see the summation of all these forces in let us suppose in model. So write it as summation of Fm, okay, divided by same forces but acting on prototype. Okay, then what you will get it as like this. Okay, you just have added up all the forces available. Okay, okay, because here we are talking about all these forces. Okay, gravity force, pressure force, viscous force. So there is another topic in this particular chapter also, the dimensionless ratios. Okay, so in a dynamic similarity, we need to understand what is this force ratios, what is this dimensionless ratios. Okay, so we are going one by one. Okay, first we need to understand what is inertia force ratio. So inertia force ratio, before going to that, just understand what is inertia force. Okay. What is inertia force? Is simple, mass multiplied by acceleration. Okay. Now here mass, how you can write mass? Mass will be equal to your rho multiplied by volume, and acceleration will be equal to your velocity divided by time. Okay. Now just take time here, so this will be equal to your volume divided by time, or you can say discharge, and we know very well discharge is equal to area multiplied by velocity. So here you can write AV, and here is velocity itself. So the inertia force is now rho L square V square. Okay. So whenever we are going to write the ratio, inertia force ratio for model and prototype, then how we are going to formulate it? Like this. Okay. FR, force ratio, or you can say inertia force ratio. So Fi model divided by Fi prototype. We just need to write the equation in this form: rho m Lm square Vm square divided by rho p Lp square Vp square equal to, you can write it as rho r Lr square and Vr square. So here you can write Fr in this form. Okay. Now what is Reynolds number? Okay, whenever we study in pipe flow, we know very well Reynolds number is a number which we can use to categorize different kinds of flow. Or you can say, if Reynolds number is less than 2000, you say that flow is laminar. If it is greater than 4000, you say that particular flow is turbulent flow, right? Now we are going to talk about what is this particular Reynolds number. Reynolds number is simple. It is ratio of inertia force by viscous force. Okay. We have just formulated what is inertia force. Okay. What is inertia force? The equation for inertia force is rho L square V square. Okay. And what? So the Reynolds number will be what? Reynolds number is what? Inertia force by viscous force. We know what is inertia force. Now we need to formulate what is viscous force. See here, we know what is Fi, rho L square V square. Now what is this viscous force? Okay. We know very well that whenever we are going to talk about a fluid flow phenomena, if there is viscosity involved in fluid layers, okay, we say that because viscosity is involved, so there must be a velocity gradient must be there. Because velocity gradient is there, that means shear stress must be there. Okay. So in any kind of fluid flow phenomena which is having shear stress, so there must be a viscous force also. How you are going to calculate that particular viscous force? It's just simple, by multiplying shear stress to area. Okay. So what is your shear stress? Mu du by dy, and area you can write it as L square. Okay. Now how we are taking a linear formation, so you can write dv by dy to v by L. Simple, because here y is length, we are writing in all the fundamental dimensions, so you can write mu v by L multiplied by L square. Here 1L get cancelled out, and what is left with us now? Fv equal to nu v L. So what will be your Reynolds number is now? That will be equal to your Fi by Fv. And here you can see rho L square V square by nu V L. So cancel out all the extra terms. What you will get as rho V L by mu, or because mu divided by rho is your kinematic viscosity, so you can write it as like V L by mu. Okay, where mu is the kinematic viscosity. Okay, so this is now clear to you. What is Reynolds number? Reynolds number is simple, inertia force by viscous force, and when you are going to formulate it, you can get the formula VL by mu. Okay. Okay, the next dimensionless ratio we are going to talk about is fraud number. Now, what is fraud number? Fraud number is again a ratio of two forces. Which kind of forces? Inertia force divided by gravity force this time. Okay, so here you can see this, you can write this as fraud number. Okay, fraud number. Okay, so we are going to define the first what is fraud number. Fraud number is simple, inertia force divided by gravity force. So we know very well what is inertia force. This is rho L square V square. Here it is well written. And what is the force due to gravity? That will be equal to mass multiplied by gravity, and here you can formulate that also as rho L cube G. Okay, so just put in this particular equation of fraud number, you will get V square by Lg. Here it is well written. Okay, now okay, fraud number, when we define it, we say that square root of Fi by Fg is actually equal to fraud number. So here you can write that square root is left here. Okay, so fraud number you can write it as Fi by Fg. Okay, so here just take a square root of this particular term also. What you will get? V by root over Lg. That will be your final fraud number. That particular root over was missed actually. Okay, so final equation for Fr is V by root over Lg. Okay, okay. So Reynolds number is over, fraud number is over. Now I am going to the third term, Euler's number. Euler's number is again it is a square root of Fi by Fp. Fi is again your viscous force. What is Fp? It is your pressure force. How you are going to calculate the pressure force? It's pressure intensity multiplied by area. So here is pressure intensity is small p and area is L square. Okay, just divide the both the formulas. What you are going to get as Euler number as V divided by root over P by rho, where P is your pressure intensity and rho is mass density. Okay. Reciprocal of Euler number is also called as your Newton number. Okay. Okay. Now the next dimensionless ratio is your Mach number. Okay. What is Mach number? Mach number is again ratio of inertia force to elasticity force. So what is this elasticity force? The formula for elasticity force is bulk modulus of particular fluid multiplied by area. So bulk modulus you can write it as K multiplied by area. Area will be your L square. Okay, so here you can write it as elasticity force Fe as K L square. So what will be your Cauchy number? Cauchy number is just a ratio of Fi by Fe. So what you are going to get here as this number, V square by K by rho. Here K by rho you can take it as root over of K by rho. You can take as velocity of sound. Just see here written as C square. Okay. Now then the next line it is written also that where C is the velocity of sound, it is given by C equal to root over K divided by, or you can say bulk modulus divided by mass density. Okay, which represent velocity of sound. Okay, so the square root of Cauchy number, okay, the square root of this particular number is called your Mach number. So Mach number will be equal to your V divided by root over K by P, or you can say V by C, simple. Okay, also you can write it as V by C. C is velocity of sound. The next is Weber number. Weber number is what? Inertia force divided by surface tension force. So how we are going to calculate surface tension force? Is simple, sigma multiplied by length. Okay, here you can get Fs as sigma multiplied by L, so that will be equal to your Fs. Okay, just take a division, you are going to get it as Weber number as V divided by root over sigma divided by rho L. This will be your final Weber number. Okay. Okay. So next is, what is your similarity loss or model loss? See, whatever kind of dimensionless numbers we have studied right now, if we apply the dimensionless number similarity in particular flow phenomena, then we'll get our model law. Let us suppose we are going to apply Reynolds number, okay, in between prototype and model. So what we'll say, that Reynolds number for particular model in particular point, that should be equal to the Reynolds number of prototype in particular on corresponding point. Okay, so that law or that statement will be your Reynolds model law. Here you can see Reynolds number of model is equal to Reynolds number of prototype. So how you are going to write it as like that? We are just equating the equations and just transfer all the terms here. What you can see here, rho r, V r, L r divided by mu r equal to 1. This is your Reynolds model law. The examples where we apply this Reynolds law or Reynolds model law, here you can see incompressible flow around structures, flow around flights, flow around submarines, etc. are the situations where Reynolds numbers are employed. See, you need to remember the situations also. You need to connect the situations with because whenever the question is given, okay, whenever the any examiner asks you that a particular flowing fluid phenomena, you need to relate what kind of model law or what kind of dimensionless model law I need to apply in that particular question. Okay, so you need to understand and you need to practice also the number of multiple number of questions, so that you can get a clear picture of this model laws. Okay, now the second is fraud model law. What you need to do is apply fraud number of model that should be equal to fraud number of prototype. Okay, so here you can see we have just equated the different fraud numbers, and what we can get is formula like that. Okay, and the examples where we apply this fraud model law is flow over spillways, sluices, and flow of a jet from orifice, etc. are the situations where fraud model may be employed. Now the next is Euler's model law. Okay, the process is simple. We need to just equate Euler number for model and prototype. Okay. In the same way, Mach model law, we need to equate Mach number for both the model and prototype. Okay, the situation where that Mach model law can be applied in aerodynamic testing and in applications involving velocities exceeding velocity of sound. Okay, I have not okay. The Euler's model law, where that particular model law can be applied where there is a high level of turbulence, so that viscous forces are less significant. So here we can apply Euler's model law. Okay. Now the last, Weber model law. The same way, okay, the situations where there is bubble formation. Okay, so and that particular cases you can apply Weber model law. Okay, so we have gone through what kind of similarities are there, and we have gone through what kind of dimensionless parameters are there, and what particular dimensionless parameters, how we can differentiate it. Okay, and how we are going to apply the different model laws which are based on different dimensionless numbers. Now we need to apply it in a particular question. Okay, so we are going to study it. See that question, problem 12.15. I have taken that particular question from your book R.K. Bansal. Okay, what that particular question says: a pipe of diameter 1.5 meter is required to transfer an oil of specific gravity 0.90 and viscosity is given poise at a rate of 3000 liter per second. Tests were conducted on a 15 centimeter diameter pipe using water at 20 degrees centigrade. See, this is this question is showing you that there is a project, okay, of pipe of diameter 1.5 meter and the tests were conducted on 15 centimeter diameter pipe. That means the first line was related to model, the first line was related to prototype, okay, and the second line is related to your model. What the question is asking again? Find the velocity and rate of flow in the model where viscosity of water at 20 degrees centigrade is given 0.01 poise. Okay, read that particular question again. Write what is given in this, what are the parameters are there and what is given in that particular equation, particular question. Okay, so here diameter of prototype is given, that there is a pipe of 1.5 meter diameter. So here dp will be your 1.5 meter. What is given? Your mu p also is given, 3 multiplied by 10 to the power minus 2 poise. Also the discharge is given 3000 liter, or you can say 3 meter cube per second. Specific gravity of oil is given, density of oil is given. Okay, density of oil you can calculate because specific gravity is given. Okay, so now this is all the given terms for prototype. Now go for the model. What are the given parameters for model? Diameter of model is given as 0.15 meter and viscosity of water is given, density of water we know very well. Okay, so when we are going to we are talking about pipe flow, obviously. Okay, so in a case of pipe flow we usually apply Reynolds model law. Okay, we know very well what is Reynolds model law, rho v d by mu, and the ratios for corresponding parameters in model and prototype, that must be equal. Apply Reynolds model law in this particular question. You can see, you can write equation like this. Okay, all the other parameters are given. Okay, just take d in place of L in Reynolds number equation. Okay, so here what you can what you know, what it is given is rho p by rho m is given. Okay, rho is given, diameter is given, dynamic viscosity is given. Okay, so find the velocity and the rate of flow in the model was asking. Okay, so you can get as Vm by Vp by equating in this particular Reynolds model formula. You can get Vm by Vp as 3. Okay, you need to solve it. You will get it as Vm by Vp as equal to 3. Now Vp, or you can say velocity in prototype, how you are going to calculate it? Simple, that will be equal to discharge divided by area. Discharge is given 3 meter cube per second. How you are going to calculate area for prototype? Pi by 4 d square, d is also given, dp is also given 1.5. Okay, just calculate Vp by equating in this particular formula. What you will get? 3 multiplied by 4 divided by pi multiplied by 2.25. what you will going to get? Vp as 1.697 meter per second. Put in the last equation Vp as this term and you are going to get V final value for Vm as 5.091 meter per second. Now rate of flow through model. Okay, when you know the diameter of pipe, when you know the velocity through pipe, you can easily calculate discharge. So discharge will be what? Velocity multiplied by discharge will be what? Area multiplied by velocity. Okay, So area again you can calculate because diameter of model is given 0.15, and velocity of model you have just calculated as 5.091. So just calculate it in particular formula. What you are going to get it as 0.0899 meter cube per second. Multiplied by 1000, you will get an answer in liters per second. So this is how you can formulate all the different kind of dimensionless numbers. How this was an example for Reynolds number law. So there are other situations also where you can apply different kind of model laws. Okay. So this is for all for today. Today's lecture will continue in this topic in next lecture. Thank you. Jai Hind everyone.